Computing confidence intervals. Let's have a look at an example. Suppose that there are over 10,000 small cap stocks that are available. Now the analyst wants to estimate the expected return for the group as a whole. In other words, she wants to estimate the population average for all these 10,000 small cap stocks. Now in reality, the analyst is not going to look at all 10,000 stocks. First of all, data may not even be available for all these small cap stocks. So the procedure is to draw a sample, and based on sample findings, she can make inferences about the population as a whole. So let's have a look at her sample. She draws 200 observations. So even though there's 10,000 small caps available, so this represents the population, she is only going to draw 200 data points from that population. So this would be the sample size. So what is she going to do with those 200 observations? Two things. She's going to calculate the mean of that sample, which is 18%, and she's going to calculate the standard deviation of that sample. In other words, how dispersed these individual observations are around the mean. And let's assume that the standard deviation of the sample is 32%. But here's where we got to be careful, ladies and gentlemen. This 32% represents the dispersion of individual observations in the sample. But what we're interested in is we want to construct a confidence interval around the mean. So I want to know what the dispersion is for the sample mean. And if that's the case, we got to look at the standard error of the sample mean. Let's pause for a second right there. 32% represents the dispersion of individual observations, but standard error represents the dispersion of the sample means. Which is more relevant here? Well, since you're trying to calculate an estimate for population mean, the relevant measure of dispersion is the error associated with means. So as a result, what we do is we take the standard deviation and divide it by the square root of the sample size. And then we get 2.26. So while individual observations dispersion is equal to 32%, the dispersion of our estimate for mean is only 2.26%. Why is it less here? Well, you can see as the sample size gets bigger, our sample mean becomes more accurate, and as a result, our standard error drops or becomes less. So now let's look at the framework for confidence interval, and we're assuming that we want to construct a 90% confidence interval, and the way to read that is as follows. We want to construct a range within which we are 90% certain that the true population average lies within. Now from the preceding LOS, we saw how the framework for confidence interval is constructed. So let's start off with our point estimate. So what's your best estimate for the population mean? Well, that would be our sample mean. It's 18%. That's my best guess because that's what my sample average was. And my sample was drawn from the population. So the next question is, if you're trying to construct a range, how far above and below would you go relative to this estimate in order to construct a 90% range? Now that's referred to as the reliability factor. So that tells us how many standard errors we need to go on either side of our estimate. Now for reliability factor, we need to determine whether we need to use a Z distribution or T distribution. Now our sample size was 200 observations, and let's just assume that's a large size. And from the preceding LOS, if the sample is large enough, then we can use a Z distribution. So if we are using a Z distribution and you are looking for 90% confidence interval, Z says that we need to go plus or minus 1.65 standard errors on either side of your estimate. So again, if you wanna construct a 90% range around the population mean, the goalposts have to be 1.65 standard errors on either side. So then the next thing is, well, what's the value of our standard error? Well, the standard error is 2.26, which we calculated previously over here. And now we're going to put it all together. So if you want to construct a 90% range around the population mean, you start with your sample estimate, and then you construct a range above and below, right? And you would go 1.65 standard errors on either side of your estimate. And each standard error is worth 2.26. So therefore, the 90% confidence interval would be represented by this range. In other words, we are 90% confident that the population mean lies somewhere in here. And that's how it works. That is how it works. So just a little more elaboration. Our best guess for population average is our sample average. However, there's 90% probability, in other words, 90% confident, that the population return or expected return or average return lies between those two numbers. And here's a visual depiction of what a confidence interval looks like, ladies and gentlemen. So here's our estimate. That's our point estimate. That's our best guess for population average. And since we were using z-values, it said if you need to cover a 90% range, you need to go plus and minus 1.65 standard errors on either side. And then what we do is we draw another axis or scale that represents the actual value. So what is the sample average? It's 18. Well, what is when you go minus 1.65 standard errors below the average? What's that? Well, if you take 18 and you go minus 1.65 there, you get 14.27. So that's where we got that. And how'd you get the 21.73 over there? Well, we just, this is on the right side of the confidence interval. So we just go up 1.65. So then let's see the math here. So you start with a 18 and then plus 1.65 times 2.26. That gives you 21.73. And that's where we got that number from. And just to wrap up this example, even though we can't observe the population mean, I am 90% sure that it falls somewhere in there. So we don't know what it is, but there's a 90% probability that it's somewhere in there. So now let's have a look at another example. Now suppose that using the exact same data as above, the analyst considers the sample size to be small. And now in real life, this is a judgment call. So whether the sample is big or small. And why is that important? Well, as we said, if you think the sample is big, you can use Z distribution. But if you think the sample is small or unreliable, use a T distribution. Now on the exam, it's not going to be up to us to determine whether a sample is large or small. They'll indicate it. So if it's small and we have to use a T distribution, they have to give us excerpts from the T table. That's the only way we can use T. Now also assume that the population is normally distributed and the population variance is unknown. So these are all telltale signs that we need to use a T distribution. And we're still asked to construct a 90% confidence interval for the population average. So it's the same process. The only thing that's going to be different is instead of using Z, we're going to use T. So what was the process? Step one, what's your best estimate for the population average? It'd be my sample average. So if my sample average is 18, that's my best guess as to what the population average is. Now to construct a confidence interval, you need to put goalposts on either side, just as we did here, right? So you start from the point estimate, but then you have to go above and below that estimate in order to construct your range. So for that, to determine how far these goalposts have to be, this is represented by the reliability factor. But because we're going to be using a T distribution here, we're going to do it a little differently. We're going to have to rely on tables. Now, to get the T critical values, now these would be the goalposts. So these would be these numbers. So if it's a Z distribution, we know these rules of thumb. But if it's a T distribution, we need to go find out what these goalposts are. So we're gonna have to look for the T critical values. That's what they're called. Now to find those goalposts, we need to specify the degrees of freedom, which is just sample size minus 1. So in our case, 200 minus 1 is 199. And we need to specify single tail area. So if you're looking for a 90% confidence interval, and here's a good visual. So if you're looking for a 90% confidence interval, right, how much area or how much probability is left for each tail? Well, if 90% is in the middle, that leaves 10% to be split between two tails. So therefore, each tail would have a probability or an area equal to 0.05. And that's exactly what we have here. So now I'm going to take you to the t-table. We're going to look for these coordinates, and then we're going to get the relevant t-critical value. So here we are. We're looking at the t-distribution. And again, the t-table just needs you to specify the area of a single tail or one tail. And the area of a single tail, it's right there, 0.05. And the degrees of freedom was 200. So we just need to triangulate, right? So go there, go there. So therefore, the t-critical value is 1.653. And that's exactly where we got this number from. So what t is telling us is, it says if you want to construct a 90% confidence interval, you have to go plus or minus 1.653 standard errors away on either side from your sample estimate. And the value of each standard error is 2.26. So then we just put it all together. We put it all together. So the 90% confidence interval for mu, we start with our point estimate, and which is 18, and then we go above and below, because that's what confidence interval is. It says we need to accept values above and below that point estimate. And we need to go 1.653 standard errors on either side, and each standard error is 2.26. So therefore, just putting it all together, we are 90% confident that the population average lies somewhere in between 14.26 and 21.74. So what was the biggest difference, ladies and gentlemen, between the T approach and the Z approach? It's right here. Everything else was the same. Our point estimate was the same. The standard error was the same. But when you use T, the reliability factor was 1.653. And that's in contrast to when we were using Z. When we were using Z, the goalposts were 1.65 standard errors away. But if you're using T, the goalposts get widened a bit. So now we're going 1.653 standard errors on either side. And then you can see the result. So if you're using Z, you have narrower goalposts because you were only deviating by 1.65. But if you're using T, you can see that the goalposts got a little wider. And again, we use T when there's greater uncertainty in the data. Therefore, we had to widen the goalposts for the confidence intervals in order to account for this greater uncertainty. So even though in both cases we're looking for the 90% confidence interval, with T, we're a little bit less certain in our estimates, and as a result, we need to widen the goalpost to account for that greater error. As a result, the T distribution is considered as the more conservative, cautious approach. Why? Because you're making room for more error.